In this video, I will go over some theory on ideal gases, and then I will show you how to use the ideal gas law. First, I have here on the top of the screen some constants, the gas constant R and Boltzmann's constant K. We need those two. For an ideal gas, the average kinetic energy can be calculated as 3/2 kT. K is the Boltzmann's constant, T is the temperature, and make sure for temperature you use the temperature in Kelvin. But the average kinetic energy of an ideal gas atom or molecule can also be calculated as 1/2 the mass times the root mean square. This is the abbreviation RMS. The root mean squared speed squared. And in ideal gases, we assume that the atoms and the molecules can move around, so they do have some speed, which means they also have some kinetic energy. But we do assume that there are no interactions between the atoms or molecules of the ideal gas. So this means that this term goes to zero. Now, I have mentioned in the past that the thermal energy is not a fundamental type of energy. It really consists of kinetic and potential. Now, since in ideal gases we assume there are no interactions between the atoms or the molecules, this one goes to zero. So the only thing you have contributing to the thermal energy of the ideal gas is kinetic energy. And if I use this expression, then I will have the number of atoms, because this is true only for one atom, the number of atoms that I have in the ideal gas times 3/2 times the change in temperature. This will give me the change in the thermal energy of my ideal gas. Now, I do want to remind you, this expression is valid for one atom. This is valid only if you have one atom. But the entire collection of ideal gas atoms, you can find the change in the thermal energy by calculating this expression. Now, for uppercase N, I will use the number of atoms. I will use lowercase n to indicate the number of mole. There are two ways to write the ideal gas law. This expression, P, the pressure times the volume, equals the number of atoms times Boltzmann constant times the temperature. This is what we call the microscopic version of the ideal gas law, because here we're using n, the number of atoms. This is what typically in physics, this is the version that is used. There is one more way to write the ideal gas law. Pressure times volume equals the number of mole times the gas constant times the temperature, and this is what we call the macroscopic version of the ideal gas law. This is what is typically used in chemistry. The differences are, there is a constant K, there is a constant R. This is the number of atoms, this is the number of moles. But other than that, the expression is similar. And I do need to mention, the ideal gas law is not a fundamental physics principle. It is just an expression that we have found empirically. We did some experiments and we found that in ideal gases, this relationship between pressure, volume, and temperature, this expression is it's valid. But we discovered it from experiments. It's not fundamental. Now, what I will show you here is, if I have my pressure volume graph, and this is a graph that is often used with ideal gases, especially if you're working with processes using ideal gases. So this is my pressure volume graph. One state, if I have an ideal gas system that has a particular volume and a particular pressure, then the way that I indicate that on the pressure volume graph is with a dot, because my system will have a specific pressure and it will have a specific volume. Now I will show you how in this, for this particular state, I can make a note, show you this dot here essentially indicates the state of the ideal gas system. Now what I will do, I will show you an example of how to use the ideal gas law to calculate some properties. Let's do that on a new board. So let's say that we have the number of moles. So we have 3 mole for this ideal gas. Let's say that we have a temperature of 100 degrees Celsius, and let's say that we have a volume of 500 centimeters cubed, and let's say that we want to calculate the pressure of this ideal gas. Now, as I mentioned, there are 2 versions of the ideal gas law: PV equals NKT, PV equals nRT. Which one you use really depends on the problem. Does the problem give you or ask you for the number of mole? Then you have to use the PV equals nRT expression. If you're dealing with the number of atoms, if that's what you have, then it's easier to work with the PV equals NKT version. Since here I'm given the number of moles, I will use the macroscopic version of the ideal gas law, PV equals nRT. Now, we do need to be careful with how we work with the units here. The temperature needs to be given in Kelvin. We have the ideal, we have the gas constant, the number of moles. For volume, we have to make sure that we use meters cubed, and then for pressure, we have to make sure you use the pressure in pascals. Now here I have the number of moles, so I can enter that the 3 directly here. I know the gas constant for the temperature, it is given in Celsius, and I need it to be in kelvins, so I need to convert that. And the way to do the conversion from Celsius to Kelvin, I need to add 273 Kelvin to my temperature in Celsius, and this will give me the temperature in Kelvin. Okay, now I got that. Now for volume, this is a bit more complicated. I want to remind you 1 meter is equal to 100 centimeters, or 1 centimeter is 0.01 meters. Now, if I want to convert centimeters cubed to meters cubed, I have to take this expression and raise it to the power of 3. So it will be 0.01 to the power of 3 meters cubed. Now, 0.01 is written also as 10 to minus 2. And since I have 0.01 to the power of 3, I need to raise that to the power of 3, and this becomes 10 to minus 6 meters cubed. And this is what 1 cubic centimeter is equal to. So to do the conversion, okay, I'm gonna use all of this. And to do the conversion for the volume, I'm gonna do 500 centimeters cubed, but 1 centimeter cubed is 10 to minus 6 meters cubed. And this is my volume. Now I have everything that I need in the correct units, and I can plug them in the ideal gas law to solve for the pressure of the gas. So this solving for pressure, be nRT divided by the volume. I know that the number of moles is 3. the ideal the gas constant is 8.31. I have a temperature of 373 Kelvin, and I'm dividing all of this, let's say 5 times 10 to minus 4. I got rid of the two zeros and made that into a minus 4. And if we do these calculations, we will find for the pressure 1.9 times 10 to the 7 pascals. And this is how this is the process that and we can use to find the pressure. I added I have 5.0 to make sure everything here has at least two significant figures. So that's how you can use the ideal gas law to obtain the pressure if you have all the other information. And what I will show you in a different video. What I did here, I showed you if your ideal gas is in one specific state. If it is here, I showed you how you can obtain some more information about your system. In a different video, I'm gonna show you how you can work with the ideal gas law if the ideal gas goes from one state to another state, meaning from one point on the PV diagram to another point, and that involves a little bit more work.